Thanks for inviting me to speak here. Let's see if I can make it work. Yes, my name is Arne Laucht, and it's my pleasure to represent Diraq here at this event tonight. Diraq is also a company that is building a quantum computer, so many of the motivations that you've heard in Julien's talk might be reoccurring in my slides today as well. So Diraq, in contrast to Nord Quantique, is building a quantum computer based on silicon spin qubits in quantum dots. And we have the humble mission to deliver revolutionary quantum computing technology to the world. This is the team. We're based out of Sydney, Australia. We are a spin-out of the University of New South Wales in Sydney. And we're now about 45 staff and 15 students. We have our headquarters, our research and development labs, all of that is in Sydney, but we've started expanding into the US, and we're about to open a small design lab in Silicon Valley and have a few activities as well in Boston. Motivation for quantum computing is really driven by applications and by the value that quantum computers can unlock in the development of, or the optimization of different fields. McKinsey estimates that in a few years, the quantum computing market will be at the order of $1 trillion. That is only unlocked when we get to the point of fault-tolerant quantum computers. The smaller quantum computers, anything that you have now, the noisy intermediate system scale, the NISQ systems, they don't really have that value. It's really only when we get to the big, full-scale, fault-tolerant quantum computers when that value is unlocked. And the estimate is that those $1 trillion kind of are split over 4 different areas. One of them is finance, where portfolio optimization or risk management are suitable applications. The second one is chemicals and pharma. So if you want to simulate molecules, you can use a quantum computer for that. And that allows you to find and discover new materials, new drugs, new medicine. The third one is transport, logistics, and automotive. So here, route optimization is a big application for quantum computers, but also, again, material design, for example, for batteries for electric vehicles. And the last one, the category of other, is artificial intelligence, machine learning, and encryption and decryption. I am a scientist by heart, not a business person, so I'd like to include some data and some plots in my talks. And this is probably the most technical part of the presentation that you will see. So what you have here, and bear with me for a second, is a plot that was compiled by DARPA in the quantum benchmarking program. And it shows the different applications and algorithms that can be solved with quantum computers and the resources that they require. What you have on the x-axis at the bottom is the system size, number of computational qubits. That is how many computational qubits or logical qubits you need to run that algorithm. What you have on the y-axis is the computation size, the number of operations that you need to execute, the number of gate operations. And there are 2 main takeaway messages here from that slide. The first one is, if you look at all of these applications, and they range from dynamics of magnetic materials to developing corrosion-resistant materials. If you look at all of these applications, the easiest ones to solve still require 1 billion operations. So you won't get anywhere with qubits that have 99.9% fidelity. That is 1 error in 1,000 operations. If you need 1 billion operations to be executed, we need much, much better computers. And that means we need to introduce error correction. We have to make our qubits fault tolerant. The second point, and if you look at these gray lines going through the plot, they indicate how many physical qubits you need to create these logical qubits. So you need 100,000, 1 million, 10 million of physical qubits of that 99.9% fidelity to create the logical qubits that are good enough to execute these applications. One example, for example, is that diamond in the middle of the plot. That corresponds to the RSA 2048 algorithm. So if you want to break the encryption, you need so and so many qubits. You need about 5 million physical qubits encoded into about 6,000 logical qubits. Came down? Okay. Yeah, these estimates are for very specific interpretation and surface code. And the field is developing. So the numbers are coming down, but the order of magnitude is still correct. So my point here is a useful quantum computer will need many, many millions of physical qubits. Now we believe that the development of a quantum computer is very similar. It has parallels to the development of a classical computer. If you think back to 1945 to ENIAC, which was one of the first computers built out of vacuum tubes, then one computer filled a whole room and could solve a very small problem. Any chip that you have currently in your laptop, in your phone, in your pocket, can solve problems that are orders of magnitude more complex than that computer could solve. And that is because these switching elements, the vacuum tubes, were changed into transistors, were integrated into silicon chip, into integrated circuits, miniaturized. Now a chip in our pocket has 1 billion transistors. The transistor is the most fabricated product or element in human history. So we believe that we can only get to these numbers of qubits if you can make use of the classical semiconductor industry, foundry technology to make them. Now, what you can see on the top, and that has not survived the export into PDF, what you can see on the top is a classical transistor, and most of you will know how that works. You have a source and a drain, you have a metal gate on top, and when you put a voltage on that metal gate, you can switch on a current. That is how that switch works, and then our computation is based on turning these switches on and off. If you change that layout slightly, you make your gates a little bit differently shaped, you add a few more, and you massage your electrostatics in the right way, then you can actually trap single electrons. Instead of having a current of electrons flowing, you can trap single electrons, and the spin of a single electron is what we use as a qubit. And then the bottom image shows how you can scale up. You can add all of these quantum dots in a line, in a row, you can make a two-dimensional array, and you can really have hundreds and thousands, up to billions of qubits on a same chip, because they're so small. They're really only 50 nanometers large. So when we started that technology about 2 decades ago, we started working in the university clean room, and we were making devices, and we could show that the technology works. We can make qubits, and they work. What we have done over the last 2 years is to take the technology and translate it into a commercial foundry. So we're working with 2 foundry partners. We're working with a research foundry in Belgium called IMEC, and with Global Foundries. And we are getting our devices, our qubits, made by the foundry partners. That is the second data slide that I kind of squeezed into my presentation here. This is some data measured on these qubits made at the foundry at IMEC. And I don't have time to explain what it actually is, but it looks pretty. And the more fringes you see, more oscillations you see, the better the qubit. That's kind of an indication of the quality of the qubit. So these ones are very, very nice. And we're looking forward to scaling it up and taking it to the next level. So by taking the qubits and making them really small, fitting them all into a transistor, our vision is to create a quantum computer that, again, fits into a single room. You can see on the bottom left, it has a cryostat. It needs to be cooled down, but we are planning on only using one cryostat. It has some racks for control electronics, for classical computation, also to integrate it into a high-performance computing center with fairly low CapEx, fairly low OpEx cost to tick really all of the boxes of the market needs in terms of high qubit count, cost effectiveness, the size requirements, and the scalability. Compared to some of the other qubit technologies, and Julien had a very similar slide in his talk, our system would be much, much smaller. It would fit into the room. It wouldn't require a whole warehouse for a single quantum computer. And the big advantage of that is that you can also build many more of those. You don't just need one quantum computer to solve all of humanity's problems. You need hundreds or thousands of quantum computers to do that. So, kind of as a summary slide, we started that technology, we invented it in 2014. We got a bunch of patents, a bunch of publications. We've recently demonstrated the operation of foundry qubits with very good fidelities and have strong foundry partners. The same as Julien earlier, we're also part of the DARPA QBI program. And the announcement just came out today, so we're very excited to work now with DARPA on external evaluation of our technology. And second big announcement, we now have 10,000 followers on LinkedIn. Thank you very much.